We'll be looking at question 16 from the June 2019 paper. This question is actually quite a few topics in this one question. Starts with Sir Humphrey Davy discovered several elements including sodium, potassium, magnesium, calcium, and strontium. The history of these elements, how they were discovered, is quite fascinating. I definitely recommend worth looking up. There's a great scientist. He does programs, Jim Al-Khalili. You'll be able to look at some of his stuff on YouTube. Chemistry, a volatile history is quite fascinating. Anyway, explain which block in the periodic table sodium and magnesium belong to. If you look in the periodic table, sodium and magnesium, they belong on the first two groups, which is known as the S block. Now, why does it belong to that S block? Because the highest energy level or the outer electrons are in the S subshell. Highest energy level or the outer electrons are in the S subshell. That's why. Next question. This is a relative atomic mass question. You've done many of these, but the trick here is that they want you to give it to 5 significant figures. I don't think I've ever seen a question saying 5 apart from this one. So, determine the relative isotopic mass of the third isotope. Aha. Can you see how they are getting more clever in, we don't know what that third mass is. Let's call that X. Relative isotopic mass. Wait a minute, determine the relative of the third isotope. So, yeah, we don't know what that is. And what we can do, we can put that X here. And the percentage abundance of it will be 100 minus the other two percentages. So what is that? 100 minus 78.99 minus 10. That's 11.01. So we know that mass times percentage, these are really accurate relative isotopic masses, 78.99 plus 24.986 times 10.00 plus X multiplied by 11.01. We get all those answers, we divide it by 100, and that equals, to the other side, 24.305. We got that from the question here. So all we do is rearrange and work these out. That's quite a few calculations for just a 2 marker. Let's do this. 23 point. One 894.57 515 249.86. I just times by 10. So what, by rearranging, we multiply both sides by 100. So this left-hand side now becomes 2430.5. Let's subtract 1894.57 515 and subtract 249 11.86. This gives you 11 point, actually, let's divide the 11.01 to the other side, 11.01. This will give you X. Whatever you do to one side, you do to the other in these calculations. Okay, 5 significant figures. I've got here, I got the wrong answer. Let me check the values. 205. Minus. That divided by 11.01. What have I done wrong here? 985. 985. 986. Let me recalculate this. 23.9. 1894, 5751. That's correct. 249.86. That's correct. All my calculations are correct. So why am I getting a different answer? So 2430.5 minus 1894.575515 minus 249.86 gives you that. Divide that by 11.01. Ah, okay. Sorry, ladies and gentlemen, bear with me. 2430.5 minus 249.86 gives you that. Divide that by 11.01. Yeah, I think I've got fat fingers. Calculator error. That gives you to 5 significant figures 25.982. Wow, so easy to get mistakes on this, what is otherwise seen as an easy question. Student adds excess of calcium oxide to water in a test tube. In a separate test tube, the student adds excess of strontium oxide to water. Right, this equation for the reaction of calcium oxide with water, state symbols are not required. Calcium oxide, when it reacts with water, it only gives you one product, calcium hydroxide. Suggest the pH of the two solutions. Now, the thing is approximate. So really, both of them have to be greater. The pH has to be greater than 7 for both of them. Why? Because it forms an alkaline solution. However, you see, calcium ions are smaller. And those hydroxide ions, they will attract far more with greater attraction than strontium will. And the reason for that is strontium is a lot bigger. It's got a greater ionic radius. So the attraction to the hydroxide ions will be less. So this will be less. Why is that? because strontium has a lower charge density. You have the same charge spread over a larger volume. That's why. So the attraction to the hydroxide ions will be less, meaning it will dissolve more easily, meaning the pH will be a lot greater. So if we call this 13.5, for example, calcium oxide will need to be a bit less than that. We could call that 12.5 because calcium hydroxide, oh, sorry, we're talking about the oxides. Apologies. Oxide, which is this, same reason. The calcium oxide will be less soluble than strontium oxide because the attraction between both of these will be greater, requiring more energy to overcome it when it's dissolving and reacting. Hope that makes sense. Moving on. We've got here the Born-Haber cycle, which is the lattice enthalpy. Born-Haber cycle to determine the lattice enthalpy of potassium oxide. Complete them. So you see the first one is the formation. Formation is where you're getting their elements in their standard state, reacting with each other to give you the product. This is your enthalpy change of formation. As you can see, the first step there must be atomization. From here to here must be atomization. So you'll get 2K, but the only difference is the state symbols. Everything else stays the same. The oxygen has already been atomized. Then you have the first electron affinity, which releases energy, which is 2K plus gaseous plus O minus gaseous plus 1 electron left. When the second electron is going to be gained, it's an endothermic reaction because you've got a negatively charged ion attracting a negatively charged electron. So you need to input energy. That's why it's an endothermic. That's why the arrow goes up. 2K plus gaseous plus O2 minus gaseous. And your Born-Haber cycle is thus complete. Double check that. Yes, yes. Yep. Yep. And yep. That's all correct. Now, calculate the lattice enthalpy of potassium oxide. You see, the general formula for this is, it's like a hack. Lattice enthalpy is equal to the enthalpy change of formation minus everything else. This has never let me down. And just to show you, we are trying to get from here to here. We don't know what that route is, but we know the opposite route. So let's go against this arrow, minus, 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 and we've got a plus enthalpy change of formation because we're going with that arrow. Yep. So all we need to do, we need to be mindful of potassium because we're dealing with 2 moles when we're atomizing it. And first ionization energy of potassium will also be doubled. Yep. So let's work this out. Minus 363 minus everything else. Let's try that. minus 363 minus 141. I've got here minus 2277. Yep, that gets you the 2 marks. Minus 2277. 2 marks. Next question is asking you the first ionization energy for sodium is more endothermic. This basically means that the ionization energy of sodium is greater. Why is it greater? We need to compare sodium with potassium, which is in the same group. We're using the DSN factors. DSN factors and how they affect the nuclear attraction. You see, as you go down the group, the atomic radius increases, which results in more shielding. And what this does is it decreases the nuclear attraction. And even though the nuclear charge increases, this effect is outweighed. So we can, it's referring to why is sodium more? So we're going from there to there. So for sodium, let's talk in terms of sodium. Sodium has a smaller atomic radius. There's less shielding. And so there will be a smaller, there'll be a greater nuclear attraction. Yeah, 2 points. You could do less shielding or atomic radius for that 1 mark. The next question, the lattice enthalpy of sodium oxide is more exothermic than potassium oxide. Explain why. You see what we've got here, we've got sodium attracted to the oxide ions and potassium ions attracted to the oxide ions. So these are the same size, but sodium is smaller and potassium is larger. So it's got an extra shell. So why is it more exothermic? Let's talk in terms of, we could say sodium ions have a smaller ionic radius. And because it has a smaller ionic radius, this is an extra thing, but I want you to think about it. So the charge density, that +1, is now spread over a smaller volume in sodium versus potassium. And because that charge density is greater, there is a stronger attraction to the oxide ion. Got the attraction there, it's going to be greater than with the potassium. That is the end of question 16. Ladies and gentlemen, I will see you tomorrow.